Thanks, and Deborah, over to you.
Okay, thank you, Daniel, and good morning, everybody, and welcome to this next session of our Supergen Net Zero Conference. Welcome to our session on Supergen Offshore Renewable Energy, where the Supergen Offshore Renewable Energy, we'd like to share our research across the hub. I'm going to start with just giving a little bit of an introduction before we get going. So the Supergen Offshore Renewable Energy covers offshore wind, wave and tidal energy. And because all of these are important technologies from the offshore renewables, which will contribute together towards the renewable energy from offshore that will support our net zero ambitions. And because they all coexist within the marine environment, there are many synergies between them. So it seemed very sensible to bring them together within a single hub. So what we're looking to do within the Supergen Offshore Renewable Energy Hub is to bring those technologies together and to advance them to take the place they should within our energy mix of the future. We take a whole systems approach, and we, as the other Supergens, we're providing that research leadership for the sector, bringing together and connecting people and inspiring research in offshore renewable energy. We've seen some significant advances in offshore renewable energy over the last few years. We've seen a real shift in offshore wind from mainly focusing on fixed offshore wind to looking at floating offshore wind. We've seen some significant new players coming into the sector, and we've also seen some significant advances in wave and tidal stream energy, but also recognise the need to really keep those two sort of less commercially advanced areas of technology, keeping them very much on the agenda because they're critical to our eventual net zero target. Okay, so
I think we appear to have lost Deborah. Lee or Kirsty, I don't know whether you could confirm that. I cannot see. Deborah appears to have frozen on my screen. So I wonder if anyone might be able to just take over in Deborah's position, or we just skip to the first of the presentations and maybe catch up with Deborah when she's able to return.
Hi, Dan. Yeah, I think we can do that. So we'll go on to Beth Scott's presentation, I think, and we'll go on to that. Deborah joins back again.
Okay, great. Thanks, Lee.
Hello, my name is Beth Scott. I'm a professor of marine ecology at the University of Aberdeen, and I'm also one of the Supergen ORE Hub co-directors. What I'm going to do here today is talk about landscapes A and G. These are the research themes. A is about resource and environmental characterization, and G is about environmental and ecosystem effects. And I think you can see that's why we've combined these themes, is in fact they really are two sides of the same coin. Both engineers and ecologists need to understand the physical resources at a range of spatial and temporal scales. This kind of data is extremely hard to get. It's very expensive, and it really would increase our knowledge and usability of this data if we considered working together to collect this data. What we're doing in our core work within Supergen is we're looking at the fine scale to the large scale physical and ecosystem aspects. And this work goes throughout work packages 1 to 5. And what I've got is an example of some of the information that we've collected and are using is the use of 3D hydrodynamic models. You can see running in the background there in this location, but also that there's been ADCP and acoustic fish school collection from the MyGen tidal site that we're using. That's at the fine scale. At the large scale, we're looking at whole information on UK waters for offshore wind. And this is an image of all of the round 4 sites in which offshore wind will be placed. So there's a lot of habitat there to understand and look at what is the best locations and within micrositing for pylons and for anchors, and of course the use of cables. But what we've also done is we've looked at these habitats and also in terms of wave and tide by looking at contrasting habitats and digging into the ecosystem types that are in these areas. And we've done that by using 30 years of historical data to start to understand the ecosystem types and also understand what climate change has been doing in these different regions to better be able to predict forward which regions might be changing much more drastically than others. Now what I'm going to do is go through a range of our flexi funds in these landscapes. And I'm going to start with the work looking at current on wave buoys. And this has been done by Samuel Draycott using tank simulations and real experiments, where he can then compare the measured motion of the amplitudes in these experiments and compare those to the predictions from a numerical model that includes currents. This is providing a new framework for predicting current and directional spectra from buoy motions. Next, I'm going to talk about the V-Scores project. This is run by Benjamin Williamson. This is using drones and is a very cost-effective, low-risk, rapid measurement technique. What you can do with this is use the images you can collect very rapidly from the drones to validate surface currents and use it as a mapping tool. And drones can be compared to data from ADCPs, ADVs, and drifters, but done much more rapidly and much more inexpensively. Also, what can happen is you can translate that information from the surface you see to predict what's going on through the water column. And this sort of information can be used in the environmental aspects as well to predict things like seabirds and mammal movement in these areas. Another one called Venti, run by Marco Placidi, is looking at the fact that the atmosphere is often in a non-neutral thermal conditions. As you go up through the atmosphere, the wind resource is significantly different and it's really affected by this, but it's often neglected in many models. So they are using the meteorological wind tunnel and they're producing then these outcomes of non-neutral winds, and they're then putting that back in to study their effect on wind farm performances. Now I'm going to switch to some ECR projects, and this is a dual one run by James Waggett and Sean Fraser. And this is using some unique ways of capturing data called your BinoCam, which takes pictures of diving seabirds and looks at the foraging behavior of animals above the surface, whereas at the same time, it's got a whole bunch of modified fish traps across the sites to be able to look at the types of animals or fish that are coming in and out and looking at both their diversity and the size ranges that are available. This is really helping us learn a lot more about how animals are behaving and why fish and mammals and seabirds are all in these areas together and so much foraging occurs. A rather new one by Dr. Andrew Want is looking at the dynamic subsea power cables and how they are impacted by marine growth. We really need to understand marine growth better because it's going to impact the functionality and the vulnerability of these dynamic cables. These are going to be used, as you know, all through offshore renewable industries. And as you can see by the picture, a lot is going to happen when you put things in the water. And this needs much, much greater understanding than we have at the moment. And last but certainly not least, I'm going to show you animation from this work by Pablo Uro that's looking at large eddy simulations performed by using the state-of-the-art digital offshore farm simulator, where he's investigating the really complex interactions between wave and tide flow and the turbulent aspects of them. So I'm hoping you enjoyed that rather quick romp through some of the projects. There's many more to go look at, so please have a look on our website for these different projects and also about the core work that we're doing. And what you can do is also then look and see if your research should be up on this research landscape, and please submit it. So hopefully that was enjoyable, and we look to see you at our website soon.
Okay, thank you very much, Beth. Thank you very much for that presentation, and apologies to everybody for my internet failing there. I think I disappeared. I'm not sure exactly where I was through my presentation when I disappeared, but I would like to just pick up on showing you a couple of slides to introduce this area. So just moving through, we're going to look through our research landscape. We're going to have presentations from members of the core team in different areas covering our research. You've just heard from Beth Scott there from the University of Aberdeen. So our role in inspiring the research, connecting people, and also promoting our research and talking to people about our research is common across all of the Supergen. So we're connecting with policy. We've got the policy session this afternoon. We talked about internationalisation yesterday. We talked about industry collaborations yesterday and the importance of those. And we also talked about EDI in our EDI session on yesterday as well, or Wednesday. So within those areas, of course, Supergen ORE are very active. We've just come back from an outreach session at the Green Man Festival, where we were talking to the general public and a whole range of people of all ages interacting with our hands-on stand activity around offshore renewable energy, with the opportunity of using a mini wave tank and actually converting the waves in the tank to make electricity. So that was very exciting. We also, at the moment as I speak, we have a host of early career researchers here at the University of Plymouth active in a masterclass to teach them about hydrodynamics and physical modelling in the Coast Laboratory. They've just recently had a companion masterclass on computational fluid dynamics delivered through the University of Oxford. So supporting those. And then Beth mentioned our research landscape. On our website, you could come and visit our research landscape, and through this interactive web tool that I'm just demonstrating here, you can see we try to put together all of the information in a summary form, and you're going to hear about the detail of this information today. So you can see we've got 10 high-level research themes there that we've identified in discussion, in consultation with industry and with academia across the whole of the sector. And within each of those sort of top-level themes, we have a number of research challenges. Those can be, they appear on the research landscape. If you click on the theme, then you can click across and get further information and further detail on each of those. We're going to hear research presentations around each of these different themes this morning. And also, following what Beth just said, we're inviting people, if you have research in these areas and they're not included there, then to please contribute your research information onto our website. So that's me, stop presenting, and I'd like to hand over to our next speaker now, and this is Professor Richard Wilden, who's going to talk to us about our research theme B, fluid structure seabed interaction. So thanks very much, Richard, and I'll hand over to you.
Great, thank you very much.
Yes, thanks. Please do put questions into the chat, and we'll take all the questions at the end as a panel session. Thanks.
Okay, so as Deborah said, my name is Richard Wilden. I'm from the University of Oxford. I'm one of the Supergen Hub co-directors. So I'm going to be trying to give you a very brief overview of some of the activity going on under Research Challenge B, which is fluid structure seabed interaction. And broadly, what this challenge is trying to capture is the very horrible, complex environment in which we try and extract energy from, be it wave energy, wind energy, or tidal energy devices. What we're really interested in is how we try and develop better engineering models, engineering solutions for things like this. This is an underwater turbine. It's sitting in a horribly complex place. It's got velocity shear. We've got turbulence and roughness coming off the seabed. We've got free surface waves going past it. It might operate in isolation. It might operate as a pair of devices. It might be fixed to the seabed. It might float from the surface. And we've got anchors, we've got mooring lines, we've got cabling systems, and we've potentially got motions of those different support structures as well. And whilst a lot of engineering tools have been well developed for individual components of those systems, where we want to try and bring things together is actually developing better integrated engineering models, engineering approaches, in order to try and actually get some of those systems talking to each other, or those modeling systems talking to each other, in order to present better engineering solutions, try to reduce reducing some of the conservatism, etc., within engineering design for all of those disciplines, wave, wind, and tidal. So I'm going to give you a little overview of some of the activities we've been doing in the core research in here, mainly around multi-scale modelling of wind and tidal devices. I'll say a little bit about some of the novel device concepts and how we might use some of these environments a little bit differently. And I will point you to one of my colleagues, Byron Byrne, who's going to be giving you some interesting look at some of the exciting work we've done on wind foundations. And I'll also highlight some of the Flex Fund projects that capture some of the other areas of interest, cabling systems, etc. So this is some of the work, and Beth related to some of this just now, about multi-scale modelling. Really, the essence of this is that single devices, or the environment past a single device, is not the same as the environment past multiple devices. And what we're trying to do is understand how, when we take particular site conditions, and here this is going to be some velocity shear and some turbulence, how we can use those site conditions to then understand what the flow and the performance and the fatigue life and then the effect on the environment is through a farm of devices. So we take those site conditions, we try and synthesize some inflow conditions for large numerical models, and here this is going to be some sort of turbulence field and some kind of wave field. We then put those things through high resolution numerical simulations. You saw a lovely video of one of those. And then we can develop whole farm models and analyses for what goes on. And we can develop models for the fatigue decay, the fatigue life of those systems, and also what happens to the flow field and the turbulence, and how that then links through to the ecology, and how that then affects the response of different species, and how those shoal patterns might move around in response to what's going on, and how the farm might be operated and the conditions it might face. So this is the idea. We're trying to take lots of different systems, put them together to give ourselves larger models that take you all the way from the site condition to what happens in an engineering and ecological sense. Another area, this is moving above water into the more mature wind area. Although wind turbines are large and there's lots of them installed producing huge amounts of power, making great contribution, we still have a very limited or poor understanding of the energy yield and the fatigue damage that some of these devices undergo when operating in large farms of devices. So this is actually moving us from a single device to multiple devices. And what you're looking at in the top here, this is the Scroby Sands wind farm, is it sort of a little analysis to give you an idea of what goes on. All these little dots are wind turbines. We're going to concentrate on this one here at the centre with the red cross. And all of these points are data recorded for the flow speeds coming at that wind turbine in different directions. And what you can see is, depending on which direction the wind's coming from, you might have a high wind speed or a waked low wind speed, because it has to transition and pass through different parts of the wind farm to get there. And this means that actually the multi-scale wind farm model is extremely complex, and it's very, very hard to actually get detailed, accurate estimates of the flow speed at the wind turbine. The forces on the turbine go with flow speed squared. The power delivery goes with flow speed cubed. So it's the engineering analysis is very sensitive to getting this right. And what's happened is, although farm models exist, they've been developed for actually quite small farms for low power devices. And as farms have got bigger and the devices themselves have got bigger, we need to develop new models that take in new types of interactions between the turbines. So working with partners, what we're doing here is we're using high resolution simulations, and this is the kind of thing you can see at the bottom here. This is a 10 megawatt rotor, and using those high resolution simulations of single and interacting turbines, we can then actually try and build new Lagrangian wake models, enabling us to look at things like layout optimization and farm control strategies in order to benefit lifetime yield and LCOE type estimates. Although those areas all relate to multi-devices, even at the basic level of a single device, we still have very challenging problems in terms of predicting the loads when individual devices are put in very complex flow environments. So one of the things we're doing through Supergen is we're running a community leadership engagement project where we're bringing academic and industrial partners together to try and actually improve engineering models for individual devices. So what we're doing is we're doing some very high fidelity experiments in a very controlled environment of an underwater turbine in waves and turbulent flows. This is a highly instrumented device, and we're then going to ask our community to try and predict the best they can what the loads are on these devices, and through that mechanism and then feeding back what the actual data is, we can then try and improve engineering models and put error bands around existing models. So this is a little sketch of the device, and to sort of give you an idea of the scale, this is some sort of average sized person. And we've got highly instrumented blades here. We've got measurements coming out all the way along the length of the blades. You can see cutouts in here. And then we've got fiber brag gratings and strain gauges down the length of the blades to try and get some loading estimates. And this is a very live project. We've just come back from doing some of these experiments. This is the turbulence grid. We're towing through a large tank with some waves coming at the device as we push it through the tank. These are the blades. You can see the optic fibers layered into the blades down here, and they all come out, all the sensors come out through the root of the blade. This is not quite the same experiment, but this is the kind of thing you're looking at, some underwater turbines being pulled through the water. We're actually launching the first of the workshop associated with this exercise next week, which we're inviting all our participants together to start trying to simulate and understand the loads experienced by this turbine. This is an ongoing project that will be running for the next 12-18 months. Also, something about the novel devices. The environment in which underwater devices exist is quite different from the air environment for wind devices. And one of the things we are trying to do is look at how we can use the constraints imposed by seabed and sea surface to actually benefit the performance of devices. It's quite a nice story. You sort of loop around from theoretical modeling through experiments into LCOE type analysis. And by taking some very fundamental approaches combined with simulation, we can actually develop models that say we can actually extract more energy by using constraint effects between turbines. We can then go and design these turbines numerically, and these new turbines here tested in the flow wave tank up at Edinburgh. And then we can see that we can get to performance differences, we can get performance uplifts from trying to operate turbines in close proximity to each other, and working with partners, industrial partners, going through to try and actually work out what the difference this makes to LCOE. So at the moment, we're looking at sort of a 10% reduction in LCOE by trying to use novel devices with environmental constraints to try and help us improve performance. So that's an overview of some of the activities going on under Challenge B. There are many more, and we've got a whole raft, I think 6 here, of Flex Fund projects across our community, and some of these are going into other areas that I haven't talked about. You can see there's some geotechnics modelling here, some piles, and there's some wave energy converters and novel devices, again flexible membranes for wave energy devices, and also some shared anchoring systems that cover both wave, wind and tidal devices as well. We've also got a range of early career researcher projects. These are smaller projects, and these range from lots of different interactions. This is a nice one here. This is looking at how the wind farm feeds back into the wave environment. So that's the opposite way around, etc. So thank you for your attention, and I will hand over to the next speaker.
Okay, thank you very much, Richard, and thank you so much for stepping in at late notice there. So thank you very much for that presentation. We're going to move across to theme CNF now, Materials and Manufacturing, and I'd like to welcome Professor Fergal Brennan from the University of Strathclyde. Thanks, Fergal.
That's great. Thank you very much, Deborah and Richard. So yes, I'm Fergal Brennan. I'm also a co-director of the Supergen ORE. I've got a particular remit, and that is as the offshore wind champion. And just to remind that Supergen ORE looks at wind, wave, and tidal power. So what I'm going to talk about briefly this morning are the research themes CNF, which are the materials and manufacturing and operations, and management, maintenance and safety. And what I'll just spend a few minutes doing is just describing some of the theme rationale and drivers, and then I'll just dip into one or two of the flex-funded projects per research theme, just to give you a taste or a flavour for the type of exciting research that is being conducted in this area. And these research themes came about through intensive workshops with industry and with the wider stakeholder community. And so the purpose of this was to produce a landscape so that we could inform our and steer our fellow researchers and colleagues across the UK university landscape to focus their research expertise, capabilities and capacity towards solving some of the pertinent challenges that face the marine, renewable energy and offshore wind sectors. So specifically with respect to, firstly, materials and manufacturing, we had identified 5 specific areas: integrity in the marine environment. And integrity, as Richard so forcefully put it, I think that offshore is a hostile environment. Of course, we've got this huge potential for energy, but also our structures get quite a battering and quite a tough time. And I'll also say, when we send people out there too, it's quite a hostile environment. So structural integrity is hugely important to ensure that the structures that are deployed in the offshore environment are fit for purpose throughout the lifetime. And specifically, we look at corrosion resistance, fatigue, and coatings and protections against these. Secondly, serial volume manufacture of complex structural systems. I'll come back to this in a minute. And then we have design for safe and cost-effective installation methods, new materials and coatings, recycling and reuse of composites. I will just refer to the offshore wind sector deal, where we had the industry strategy that was set out in collaboration, the UK government and the devolved government in collaboration with the wider stakeholder community, agreed a roadmap towards 2030. And that is currently 40 gigawatts of offshore wind by 2030. And given that we have just over 10 today, and it's taken us the last 20 years to design, build, and deploy and operate these 10 gigawatts, we've got to quadruple what we have in just under 9 years, which is quite a challenge. 60% local content, hugely important. So whereas we can slap ourselves on the back in the UK of being currently, and probably not for long because China is fast approaching, but currently the largest operator of offshore wind in the world. However, the majority of that hardware, if you like, and is not manufactured in the UK. And there's a huge opportunity as we quadruple the amount of offshore wind, and as we start to develop the marine renewable energy industry, we need to focus more on what can be done. So looking at the macro elements, and very much our colleagues and in Edinburgh very much looking at GVA, macroeconomic elements, but this also feeds in very, very much into the Supergen activities in promoting advanced and serial manufacture and volume manufacture within the sector. And hugely importantly is the target of a third female. We cannot afford not to benefit and utilize half of the available resource to us. We need the brightest and best brains if we are to achieve the aspirations that are associated with us tackling this climate emergency. The next item I just want to mention is safety. These are just illustrating G+, who produce the accident and safety statistics, and we track these. On the yellow, these are the offshore wind safety statistics shown as total recordable injury rates per million hours worked, benchmarked against upstream oil and gas. They are different sectors. All that we want to show from this is that it is a hostile environment. What we need to do is avoid putting people out there if not absolutely necessary. G+ and the industry are working hard, and you can see they are improving total recordable injury rates. But everybody appreciates that when it comes to health and safety, the job is never done. And then the other aspect is the circular economy. We don't want to see this continuing into the future. Glass fiber is notoriously difficult to recycle, and I'm delighted to be able to report that Supergen ORE has contributed significantly. Once and I will mention a couple of the projects that are associated with this, so that we can reuse the huge amounts of glass fiber that is used in both onshore and offshore wind, and also for marine renewable energy devices. So here is a list under the materials and manufacturing thematic challenge. And the first one there is as I was just mentioning, recycle composite wind turbine blades for high performance composite manufacturing. And it's not just a challenge of recycling, but what Dr. Liu Yang is doing at Strathclyde is he is developing a hugely efficient way at ensuring that these can be reused also for structural applications. So very often when you recycle, there's a certain amount of degradation associated with the structural properties associated with the material. And by being able to do this in a clever way, you can potentially retrieve almost 85% of the structural capacity as what the virgin or the parent material might have had. I'm not going to go through all of these in detail. I simply don't have time, but these slides will be available, and also there is a nice description under each of these projects on the Supergen ORE website. Here is one from an example of an excellent review that was led out of the University of Exeter on the current status and future trends in operation and maintenance of offshore wind turbines. And it's absolutely essential that these broad reviews are conducted so that we appreciate the baseline from which we operate. This is another exciting development from a Flex Fund project that was funded from colleagues at Cranfield University, and this is using additive manufacturing. And to those of you who aren't so close to this area, this is like 3D printing, and it is 3D printing potentially for the repair of offshore wind structures. So if we can go out there and use our autonomous and remotely deployed inspection methods, and we find defects, we can simply send out a 3D printing type device and repair that component or structure in situ, and that then helps us extend the lifetime and the usable value of that high value asset. And then with respect to research theme F, which is the operations, management, maintenance and safety, which is very much a continuation and related aspect to what I was just discussing. The Flex Fund projects that we funded through here was the one that was led out of York University, autonomous biometric robot fish for offshore wind farm inspection. We also have the satellite climate observation for offshore renewable energy cost reduction, led out of the University of Edinburgh with Strathclyde and others contributing, and also a couple of super projects from Exeter. Just very quickly, this is the satellite data, and this is really to look at both short-term and medium-term and longer-term predictions of the local environmental conditions that our marine renewable energy and offshore wind devices are likely to experience. As Richard said, there's a great deal of uncertainty associated with knowing precisely what the local conditions are, and the more and more knowledge that we can get, we can better prepare, we can better design, but also we can ensure that our control systems are ready for the environmental and weather conditions that we're likely to experience. And then lastly, but certainly not by least, this is the project on the robo-fish, if you like, the bio-inspired autonomous underwater vehicle. And again, you can see what the motivation for all of this is that if we can replace humans, if we can replace putting people out into this hostile offshore environment, then that will in turn mean that this is a safer, more responsible sector. And not least, this also fits into the macroeconomics, because as I say to people is when they complain about removing people and they say they'll lose jobs, my view is very much that we should not be training technicians to repair offshore wind and marine renewable energy devices. We should be training people to repair the robots that will repair the offshore wind and marine renewable energy devices. So I think that is it. Thank you very much.
Thank you very much, Fergal. Very nice overview of that area of the work. And I'd just like to remind everybody that we, so through the Supergen ORE Hub, we are supporting research through our flexible fund scheme. That is research projects of up to 100,000 EPSRC support. We've funded 30 of those, and you're hearing about those as we go through. So we've invested 3 million in flexible funded projects. And within those, we have secured 2.6 million in industry match. So they're very much collaborative with industry. Then we also have our early career researcher research fund, and that is a level of 5k EPSRC contribution per project. And in that area, we funded 25 projects with a total of 130,000. And again, you're hearing about those projects. So we're presenting across the whole range. Then I'd also like to mention, you may have seen in the chat, we're having some problems with the chat. We'd like to take your questions. We'd like to discuss the questions as a panel at the end of the session. But we're having some problems with the chat. You can, I think, work around it by going through the calendar invite on Teams, or alternatively, please could you email questions to the Supergen ORE Hub email address, which Kirsty has posted in the chat. Okay, so thank you very much indeed, Fergal. And now we'll move on to the next presenter. This is Professor Xiaowei Zhao from the University of Warwick, and he's going to talk to us about research theme D, which is Sensing, Control and Electromechanics, and F, O and M.
Thank you, Deborah. Hello, everyone. I'm Xiaowei from University of Warwick. I'm also one of the co-directors of the Supergen ORE Hub. So I share my screen now. Okay. It seems got some problem. Oh, what happened? Okay, it works now. I will give an overview on the research theme D, Sensoring, Control, and Electromechanics. This research theme mainly including 4 research areas. I'm going to briefly introduce them with examples from recent work of the Hub. The first area is control of ORE farms, which is to develop and validate control technology for ORE farms to balance competing requirements such as maximizing power generation, reducing fatigue load, and minimizing environmental impact. Next, I'm going to give several examples in this area at both farm level and the turbine level. This slide is about our recent work regarding intelligent wind farm control while deep reinforcement learning. As shown in this photo, the power generation process of the upstream turbine leads to wicks, which significantly influence the power generation of the downstream turbines, and therefore influence the whole farm's power generation. This issue has drawn wide attention, but existing wind farm control methods are usually model-based. In practice, it is very difficult to derive a control design model with reasonable accuracy and dimension for the farm-level control design. So the existing model-based wind farm control methods commonly lack adaptability and robustness to modeling error and stochastic environment conditions. In this project, we designed a deep reinforcement learning based control algorithm to address these challenges. The algorithm allows us to employ only the available data measured at the turbine rotor, including the wind speed and the power output, to learn the black box information. And our method is totally model-free, which does not rely on any analytical models. It has a strong adaptability to the modeling error and robustness to stochastic environment. So we tested our algorithm with different dynamic wind farm simulations as shown here. The results indicate that over 30% of the farm level power generation increase compared to the conventional grid strategy, and our method performance surpassed other advanced control methods such as nonlinear MPC and another very popular reinforcement learning algorithm, DDPG. Now let's look at some results at the turbine level. This slide is about vibration and power regulation control of a floating wind turbine. The motion of the offshore wind turbine platform can cause big issue to the turbine structure and power generation. Thus, its vibration reduction is very important. The traditional pitch control is effective for vibration reduction at the expense of interfering with power generation. So in this project, we developed a LPV pitch controller for the floating wind turbine, which can tackle the power regulation and the platform vibration in a synthetic manner. This slide shows some results on structure control of very large floating structure platform. The very large floating structure can allow for the operation of multiple turbines. However, like the standard platform mentioned in the previous slide, the structure vibration is a major concern of this very large floating platform. But apparently here, it is not realistic to use blade pitch control for the vibration reduction. So we employed the tuned mass dampers to mitigate the vibration of this type of platform, which achieved 33% vibration reduction with tuned mass damper weighted around 4% of the whole platform. The second area within CMD is the smart sensor system used, which is to identify, evaluate, and validate sensor technology, data transmission, integration, and interpretation system to support the improved control and management. An ongoing work within the hub is looking at the sensor distributed across ORE structure, particularly the wind and the tidal turbine blades for a number of applications such as defect detection, manufacturing process monitoring, and control. This work is led by Professor James Gilbert at the University of Hull. The example shows a 1.6 meter tidal turbine blade with 24 fiber optic strain sensors. It was designed and manufactured by Oxford University, as shown by Richard just now. Initial results show that it is able to monitor different loading conditions. Another ongoing work in this area is a flexible fund project led by Professor James Windmill from University of Strathclyde. This project designs and manufactures a 3D printed piezoelectric sensor and explores its feasibility in providing partial discharge detection capacity for large-scale floating arrays. The next example is about how to use the sensor data. With measured data and physics-informed deep learning, we can reconstruct the whole flow field in front of a wind turbine. I'll show you two videos. So this is ground truth, and this predict flow field. So these two videos show that shows a comparison between the ground truth and the reconstruct flow field. You can see they agree very well. The traditional machine learning method can only predict the wind velocity where there are measurement. So this dot are placed there are measurement. But our method can predict the wind velocity in the whole flow field, anywhere in the whole flow field, because our machine learning method is physics-based. The third area within CMD is about the drivetrain design, which is about the conception, design, and validation of novel drivetrain for ORE device, including hydraulic drives and direct drive generators. An example regarding the hydraulic drivetrain is that we studied the power generation control and grid integration of the hydraulic transmission, wind and tidal turbines. An example regarding the direct drive generator is a flexible fund project led by Professor Alastair MacDonald from University of Strathclyde. This project is developing a digital twin technology which combine transfer learning and the physical modeling for the direct drive powertrain conditional monitoring. The final area within CMD is a power electric conversion. which focus on improving the power electronic converter in order to improve the system reliability and performance. One example in this area is a flexible fund project led by Professor Li Ran from University of Warwick. This project is to develop a technology to provide a transit overload capacity to power semiconductor in the converter ORE system. This has been demonstrated by integrate the liquid metal phase change material into the package of the power module. The power module can now be overloaded to 240% of the rated current for at least 3 seconds. This fully satisfies the requirement of the grid support during a short circuit fault. Simulation shows that the fatigue stress in the pitch mechanism of offshore wind turbine can be reduced by around 10% by using a simple on-off control mode of the overload capacity to allow cooling. The ongoing work to combine this capacity with pitch control itself could show more effectiveness. I believe Professor Li Zhan will show this new result in the next assembly. Thank you very much for your attention. Oh, my.
Thank you very much, Xiaowei. Excuse me. Thank you very much for that overview of the theme. That's really interesting and great to see those new research projects coming through. Let's thank you for that, Xiaowei. Let's move to the next presentation now. And as I said before, we're going to take the questions all together at the end. So we'll have a panel session at the end and take questions then. Please do email them to the Supergen ORE Hub email address, which is in the chat, because we're having some problems with the chat. So now I'd like to introduce Professor Byron Byrne from the University of Oxford, who's going to talk to us about research theme E, survivability, reliability and design. Over to you, Byron. Thank you.
Thank you very much, Deborah. I hope you can see my slides. So
yes, yeah, all good.
Good. So I'm Professor of Engineering at the University of Oxford with a special interest in geotechnical engineering, which is really about the ground and structural interaction with the ground. And for this problem, it's about the design of foundations. I'm going to talk more widely than that. I'm also responsible with Richard Wilden for the ECR activities, and we've been very keen to hand out the ECR funds. And as you've seen through the talks, there's been a number of very interesting early career researcher projects. So I'm going to talk a bit about our work on survivability, reliability and design, and it interacts a little bit with theme B, where Richard talked about fluid structure, seabed interaction. But what we're trying to do is take a more of a holistic view across different devices, different energy generation activities, and looking at where the synergies lie and where individual techniques are required rather than things that can spread across. Now, of course, offshore renewable energy can build on many years of experience and expertise from the oil and gas sector. However, the problem does differ quite a lot, and so there are new techniques that are needed specifically for ORE, and specifically to look at the sort of design for example, the floating wind problem, where you may have many devices across a large site. And so you need to have individual designs for each of the devices, but then optimize that across the whole site. And then you need to be concerned about the fact that the environmental conditions across the site, which is very large, can differ quite a bit, particularly, for example, that the soil profiles can change across a site, which might be many hundred kilometres across, and even the water depths could vary. So there's areas where you need optimization at an individual location, but you also need to optimize across the site. And we're trying to explore techniques for developing those design approaches. One of the things that we're really interested in is design for extremes, because that really controls a lot of the design condition. And one of the approaches that we're looking to develop further are probabilistic approaches, so that we can try to assess, what is the 1 in 25, what is the 1 in 50 year calculation required, looking at probability of failure of components and of systems and so on. Now on this slide I show a number of different designs from fixed structures, floating wind structures, underwater turbines, a point absorber, a sort of hinged raft type marine energy or wave energy device. We've got an anchoring system here, we've got a mooring line and some sort of foundation device. Here we've got an anchor in the ground. We could also have a fixed foundation such as a driven pile. All of these areas are being explored by the hub, and we're also looking at all of these different ideas around the design. So we need to consider things like the whole life of the design. What happens at end of life? Do we decommission? Can we repower? And so on. So we need to bring that into the thinking. I've talked a little bit about extremes. We've got to design for extreme. We've got to be able to predict the extreme. That requires a probabilistic approach. We might need to also worry about fatigue problems, because these devices are being exposed to many, many hundreds of thousands, millions of cycles from the waves and from the wind. So we need to understand about this very harsh environment. I'm going to talk a little bit about some of the core research and some of the flex funds, not in a huge amount of detail. That can be obtained from the website. I'm going to focus here on work at Plymouth, which is looking at the design of 3 different devices, which are shown here. The first is a sort of point absorber, where we have some floating type structure at the top connected to the ground, and the relative motion between the 2 parts leads to the energy generation. We've got some sort of hinged device here where this is looking from the top, where the relative motion of the 2 parts leads to the energy generation. And then we've got the floating wind device. And so the idea is to look at these different devices. They've been selected in collaboration with industry and other partners. And what we're trying to do is assess performance under extreme conditions, and in particular here, extreme waves, and understand, for example, what are the loads in the mooring lines or in this connection here, so that we can design the system to survive for the 25 or 30 years. Before we can do that, we obviously need to understand a little bit more about the site. So Beth talked about the environmental conditions. We need to translate that into some sort of engineering model of the site. And in particular, we might want to know what are the wave heights at that site, and what is the period between, for example, the crest of the waves or the trough of the waves. And then we might want to know that over 30, 40 years, so that we can design the system appropriately. So here is a plot of wave height against period for site, the EMEC site, showing the results of a model that produces the combination of wave height and period for many years. What we want to try and do is estimate, for example, what is the 50-year extreme event, and that is given by this contour here in green, which shows that the likely distribution of wave heights and periods for a 50-year event. And actually what we really want is the most extreme bit, and that's given by this bit here. And so we could use this as input into the design. We can take that information and look at how we can create a design wave to speed up the design. We don't want to simulate 50 years of data. We want to simulate simply the event around the design extreme event. And there are a number of different techniques that have been developed, mathematical techniques listed here. So we can take that sort of information and for example, if we can use and develop these synthesized extreme events, we can move away from having to simulate irregular waves in which we have extreme events embedded. And you can see here, this is a sort of a wave elevation over maybe 9 or 10 minutes, we can try to create from a mathematical model a representation of those extreme events, and then embed that into a random background of wave heights to create a much shorter subset of the wave elevation, which gives us the extreme event from which we can then carry out many experiments or numerical simulations of that extreme event to develop the appropriate statistics so that we can understand statistically the performance of these designs. And so at Plymouth, they have laboratory experiments ongoing where they are simulating. Here you can see at the top right the point absorber and some extreme waves being generated. The middle one is the raft, and also there's numerical simulations ongoing. And the whole point is to synthesize all this information into design recommendations for the industry. From these types of experiments and simulations, we can get information on the mooring loads. And so colleagues at Southampton are doing a lot of work on development of new theoretical models into anchoring systems. So these are in systems in which you embed the anchor in the ground. My colleagues have developed a new idea for improved understanding of how these anchors can carry load, and this leads to an increase in capacity compared to previous understanding. And also, if we take account of the whole life of loading of the system, we can start to see that you might get benefits from the sort of repeated loading that occurs on the foundation, that you start to strengthen up the system, and so that can be beneficial for us. All of this then gets embedded into simple mechanical type systems that allow us to develop a simple analytical model that can be built into a numerical calculation, or simplified numerical calculation. Other work, this time from the University of Oxford, working with Imperial College London, we've been carrying out some large-scale field testing for a number of years, and through some funds available from the ORE Hub, we've been able to extend that program of work. This type of work costs a lot of money, millions of pounds. We've been able to extend that type of work to explore cyclic loading on the foundation. So this just shows some examples. These are the piled foundations that are being installed. This is a detail of the experimental work. It's very complicated, involves big forces up to many tons of load being applied. Here are some cycles being applied to our foundation. So I'll finish off with the Flex Fund projects. There's a range of these smaller scale projects looking at extremes of load, novel devices, fatigue calculations, foundation design, building on some of the other work, and also new techniques for estimating the performance of foundations during installation, and the early career researcher projects, actually looking much more at novel devices and trying to develop new ideas around that generation of energy. So I'll finish there, and thank you very much for listening.
Okay, thank you very much, Byron, and thank you to all the speakers for some really great presentations there. I think I'll invite the speakers all to join me on the panel now. If you could put your cameras on and unmute the microphones, and then we've got a little bit of time. We've got about 10 minutes where we can take some questions from the floor. Excuse me, we have had some problems we are still having some problems with the chat. So although it looks like some people are able to put comments into the chat. So if you do have questions, please put them to the chat, or please do email them to the Supergen email address. I think you can see from the presentations there the range of the research that's active across the ORE Hub, and also a lot of that research is applicable across a range of technologies, so not applicable across offshore wind and wave and tidal in some cases. And it's really great to see the early career research ideas coming through as well, some of those very, very innovative. So I'd like to sort of start off the discussion really with a question for the panel, which is around the context of this conference that we're running at the moment around COP26 and the opportunity and the challenge, if you like, of international leadership that the UK has at the moment, and the opportunity to make a real statement, or to make some real advances and some significant opportunities to make a change and to help our global aspirations towards the very, very critical and very immediate moves that we need to make towards getting to net zero. So what are the key messages that we need to be promoting here, do you think, in offshore renewable energy, given where we are, where we've got to, and what the challenges really are? So I think, I mean, I'd like to put that question to everyone on the panel, really. I think it's something that we all need to be thinking about. Shall I go first to you, Beth? Are you happy to start off with that?
Sure, I can do that. I think what springs to mind and what you've seen in these presentations is the whole systems approach. I think the Supergen group has been absolutely unique in looking at across all of the different types of instrumentation, but then trying to put it in the round in terms of the environment and also the financial aspects and jobs. And I think that is what really needs to be the message for net zero. You'll see it in a lot of other aspects, the idea of just transition. You can't have a just transition unless you understand all aspects of what's going on. And therefore, this whole systems approach that we've had within the Supergen, and that we've the ECRs and the flexible funds have also represented, has, I think, been really beneficial. And hopefully it's an example to the world of how to do it, thinking in the round, thinking ahead, getting everybody involved.
Okay, thank you very much, Beth. Yeah, absolutely. And the whole systems approach we're taking here it is really important part of that, thinking about all of the different actors and aspects and interactions that offshore renewable energy will have. Of course, a lot of that is unknown, and we need to project and predict into the future, and that's why we've got so much focus on those predictive models and connecting those different models together. Richard, can we go to you?
Yeah, I mean, I think it's the offshore renewable activity and academic and industrial activity in the UK has been at the forefront intellectually for quite a long time, and we've had great leadership in these areas, and it's time to sort of export some of that as well. And I think a couple of really important aspects about this is actually the training of individuals and the training of people. So we're very active in this whole network with the early career researchers, and that's pulling people through and training tomorrow's researchers, tomorrow's engineers. And these are these are the people that are going to be able to take these things out, not just within the UK, but around the world, and try and actually implement some of the exciting and innovative science that's coming out of our research, not just in the UK, but wider. I think the other thing that comes off very strongly, I mean, the way all our challenges are interconnected. I mean, these are engineering problems, perhaps like no others. They are so interconnected and so multidisciplinary, not just in the engineering, but into the environment, the ecology, and everything else, and policy and societal aspects, that it reinforces the need for collaboration at all levels. Not just in modelling, but in testing and policy development. And I think we've really got a strong role to play in those areas, and have got a good track record in those areas about setting the policy and the agenda internationally.
Yeah, thank you very much. And there'll be more discussion on the policy side later on in the session this afternoon. And I think, collaboration, obviously within our area, there's an enormous amount of collaboration to be done, but also across the Supergens. And again, this conference is a good example of that. So let's go to Fergal next.
Yeah, sure. Just echoing what Beth and Richard have said, I'll just add to this is that I want to, I suppose, underscore both the scale of the challenge that lies ahead, but also the absolute urgency. I don't want anybody to get the view that we're there, or that we've cracked it, and that net zero, is necessarily achievable within the timescale set. I think we have to take the message, and we have to give the message, I think, very much that the noises that are being made by governments, our own governments, both UK national and devolved government, are all very positive. It's now incumbent on us, the scientific community, our engineers and scientists, to just get on with it. And we've got to, we've got to give credit to UKRI, EPSRC for, funding this initiative. I'm very proud of the fact that we have reached out, we are reaching out and showing that thought leadership. But I'm hoping that audience is getting the message that we're open and inclusive, and we not just need everybody here to contribute. We need this 10, 1,000 times, 3 orders of magnitude more than what we're doing at the moment. And so there is no real competition in here, but it's all hands on deck, and we need the brightest and best people to join in. Truly exciting as well, truly exciting period ahead. But I am. And I'm not going to apologize about this. I'm scared. The numbers are huge, and we have to get on. The solution is not wind or wave or tidal or bio or whatever. It's all of the above. We need everything together, and we need it at enormous scale.
Absolutely. Thank you, Fergal. That importance of diversity across all of our thinking actually is important, but certainly within the energy mix of the future, we can't rule anything out. We need to keep everything in the mix. Okay, Xiao Wei, would you like to add anything?
Okay. I think the cross Supergen Hub collaboration is very important. In addition to these joint events, more joint research collaboration will be great. This can help us to understand each other's work, so that we can have a whole system view.
Okay, yeah, absolutely. And it's collaboration across disciplines, it's a collaboration across sectors, and it's collaboration internationally and across academia and industry. Byron, would you like to?
Well, I mean, everyone said quite a lot of things that I very much agree with. I mean, it is a colossal problem that we're trying to solve. And it is a problem which engineers can make a huge contribution to solving, particularly in the area that we're working in, which is ORE. But we do need more people. It's just the scale of what we're trying to solve requires a lot of very skilled and technically knowledgeable people who appreciate the multidisciplinarity of the problem. And I think that to me is the key. I mean, I think there is obviously this fantastic opportunity. It's really exciting area to work in. It really should appeal to the next generation of university students. But we need these people to come into the sector, not just in the UK, but across Europe and across the world. We have a great base, but I think we can't be complacent. We have to really, move it forward at great pace and take the momentum. And that may require quite a bit of investment by governments and taking a bit of a leap. I think in areas, wind has momentum. There are viable technologies that are being deployed, but still there's innovation required there, particularly in floating. But areas like wave and tidal need a bit of a sort of leap of faith, an investment, and we need to encourage people to say, come on, let's get on with it. We've got tools to design things. We can connect them up. We've just got to get on with actually building a lot of these devices, around the world and getting experience in the field so that we can then rapidly deploy into the future. Okay. That would be my message.
Thank you very much. I think that's a really great set of responses there and answers, and I think that's really covered the position. It's a very, very exciting area. We've made some excellent progress, but we're not there yet. and there's a lot more that needs to be done, both on the technology side, but also very importantly, looking at the environmental and ecological interactions as well, and what that looks like in the future. Okay, and I think a very, very strong message there around training and also around collaboration very broadly, and of course around diversity in the energy mix and also in the workforce. Okay, well, thank you very much. We're just over time, so I'd just like to thank you, the panel, very much indeed for your presentations and the discussion today. I'm sorry that we haven't had a very effective chat, but I hope I hope that you've enjoyed the session. And I'd just like to mention the other sessions we've got this morning. So we've got the Energy Network session, which starts at 10:45. Then we have the Super Solar Hub session, which starts at 1 o'clock today. And then this afternoon at 2:30, we have the policy session, and I look forward to seeing everybody in the other sessions today. Thank you very much for your time. Bye-bye.
Bye.